my name is Professor Rad, and this is Precalc video 314, sinusoidal graphs, graphing with a phase shift and a reflection. So this video is the culmination of all of our graphing videos for sinusoidal functions. So if you haven't watched any of those, you may want to do that before you watch this one, because we're going to be building on the techniques that we did in those videos. Primarily, we'll be building on our sinusoidal functions a sine omega x minus phi and a cosine omega x minus phi, where omega is a positive value. And we have these four formulas here: amplitude, period, phase shift, and key points. We'll also want to be using either the sine or the cosine curve to help us graph our function. So for this video, we're going to start out, well, I did that last time too. We're just going to be graphing one example. So we're going to be graphing f of t, which is 1/2 sine of negative pi t minus 5 pi. So to begin this example, we need to check to make sure omega is positive. And once we have a positive omega, then we can go ahead and identify a, omega, and phi. So omega is the coefficient of x, but this time, since our argument is in terms of t, it's the coefficient of t. So omega right now is a negative number, can't have that. So remember that sine is an odd function. So that means if I have sine of negative theta, that's going to be negative sine of theta. So if I rewrite this function as 1/2 sine of negative and factor that out from those two terms, I get pi t plus 5 pi. And now I can rewrite it using the odd property. So I can get rid of the minus inside if I throw a minus on the outside. So we have negative 1/2 sine of pi t plus 5 pi. Cool. Good start for this function. Next, we're going to identify a, omega, and phi. So a is this negative 1/2. Omega is the coefficient of t, which is now pi. And phi is what we're subtracting from the variable. So because we have a positive 5 pi, that means we're subtracting a negative 5 pi. So remember that the sign for phi is always going to be the opposite sign of what we're doing here. All right, so that's our first stage. We've written it, so we have a positive omega, and then we've identified these three values. Next, we want to figure out all these things. So we want to figure out our amplitude, the period, the phase shift, and key points. So let's go ahead and work on that. So for the amplitude, that's going to be the absolute value of a. So that's the absolute value of negative 1/2, which is 1/2. The period is going to be 2 pi over omega. So this is going to be 2 pi over pi, which is just 2. The phase shift is going to be phi over omega. So that's going to be negative 5 pi over pi, which is negative 5. And then our key points, this tells us how far to space out those points we graph for sine and cosine. We can use either the period divided by 4 or pi over 2 omega. So I'm going to use pi over 2 omega. You can use what you like, as long as it's one of the two correct formulas. So we'll do pi over 2 omega. So omega is pi. So I have pi over 2 pi, which will simplify to 1/2. Okay. So that's sort of our second phase, is figuring out those four values, because these values will help us to know where we're going to start the function, where we're going to be indexing the vertical and horizontal axes by. So let's look at the vertical axis first. So we use the amplitude to help us with the y-axis. So because our amplitude is 1/2, That means I need to go at least up to +1/2 and down to -1/2. So I think I'm going to count by quarters. So this is a quarter, so that makes this 1/2. And that will make this 1. So -1/4, -1/2. And then -1 would be down here. So the amplitude helps us to index that vertical axis. Next, we're going to use the period, the phase shift, and the key points, but primarily the phase shift and the key points to help us know how do we index our horizontal axis. So we want to have a common denominator for the shift and for the key points. In this case, my key points are going to be marked every 1/2. So, and my phase shift is a whole number. So I can use a denominator of 2. So I'm going to use 1/2 to index my horizontal axis. So each line I'm going to use to represent 1/2. So I'm going to call this 1/2, and then this one is 1. You could also write 2/2 if you wanted to. This time I'm going to use the whole number values. So then we have 1/2. So here's 2, 3, 4, -1, -2, -3, -4. All right, so now we've got the t-axis and the y-axis labeled. So our next step is to get our starting point. And this is where things now start to diverge from what we looked at in the last video. So for our starting point, there are a lot of things that are messing up the starting point for this function. One of them is the phase shift. So our phase shift is at -5. So that means for our sine function, sine usually starts at 0, 0. So because of that phase shift, we're going to be starting at -5, 0. Something else that's going on in this function is that we have a -1/2. So we have a -a. What that means is typically the sine function is going to come up and then down. But because the a value is negative, that means we're going to be flipping it vertically. So we're going to go down and then up when we go to draw our sine function. So this is because we have a -a. If we had a +a, we would come up and then come down like usual. So those are two things that are messing up this function a little bit. Here's the third one. When we drew our axes, we didn't get to -5. And that's where we need to start. So this is a bit of a problem, especially if you've been given a specific graphing space to graph on, or like what if our phase shift ended up being like -72? I don't want to have to draw all the way down to -72 when I need to know where 1/2 is to plot my key points. So you want to try and balance all of these things. So the good news is, remember that sinusoidal functions are periodic, so they're going to repeat themselves. So if this starting point is literally off the charts, we can find a new one by either adding or subtracting the period. So because our period is 2, I'm going to add the period. So I'm going to add 2 to that x value to get me a new starting point. So I'm going to add -5 plus 2, and that's going to give me -3, 0 as my new starting point. I could also add another 2 here, and that would get me to -1, 0. So if I wanted to, I could start at -1, 0. That would be another option for this function. So for us to practice this, why don't we start at -3, 0, and then at the end we'll check to see if we would have gotten the same function if we had started at -1, 0. So we can test this hypothesis. But the period tells us how far we need before we're going to restart. So if your starting point is not on the graph, just amend your x value by adding or subtracting however many of the periods that you need. So I'm going to start at -3, 0. My key points are plotted every 1/2. So that's going to be every single interval here. because I counted by 1/2. I'm going to go down first. And because my amplitude is 1/2, that means the peak is going to happen at the 1/2. So my next point is going to be here at -2.5, -1/2. So just to reiterate, it's going to be negative because we're reflected, so we're going down. It's 1/2 because that's the amplitude. And then this x value of -2.5 is coming from the fact that our key points have to happen every 1/2. Once I get started with my sine curve, now I can go ahead and plot the other points following this pattern. So the next one's going to happen here at -2. Then at -1.5, I'm going to go up to 1/2. Then we have -1, -0.5, -0.5, 0, 1/2, 1/2, 1, 0, 1.5, -0.5, and we'll just keep going. It's really squeaky marker. Yeah. And then once we have all of those key points plotted, we can go ahead and connect them in the traditional sinusoidal fashion or manner here. Let me draw this up. Well, I left out part of it. Yeah, so let's draw our sinusoidal function. All right, there we go. So let's check a few things. Let's check it against the period. So within the period, it should have occurred, we should have one full cycle. So between 0 and 2, we have one full cycle of the sine function. If I had started at -1, 0, would I get the same graph? Well, I would have started at this point, and then I would have gone down because of the pattern. So I would have gotten exactly the same graph. So that would have worked as well. My amplitude is 1/2. So it's all looking pretty good. So what this is also illustrating to me, though, is that this function was written much more complicatedly than it needed to be. Notice that if I didn't incorporate a phase shift, I would actually just have the normal sine curve. So I wouldn't have needed that vertical reflection either. So another way to have written this sine function would be to have 1/2 sine of, let's see, it looks like pi t, right? So if I use pi as my omega, so if I keep that, so I have the same period, now that just looks like my usual sine function. So this expression and this one here are the same. So sometimes when you go to graph a sinusoidal function, you also notice that there were easier ways to express that function than what we were given initially. So this is going to conclude our graphing of sinusoidal functions. In our next set of videos, we'll be going through some more algebraic techniques. So we've been digging into some properties of trig functions. In the next videos, we'll be looking at some additional trig properties. I was laughing at an internal pun because we're going to be looking at a sum and difference formula. So it's an additional formula because it's a sum formula. I think that's time for me to wrap this up. So I hope you have a magnificent day. I hope this helped you to graph some sinusoidal functions, and I will see you in the next one. Bye for now.